car, you want to maximize the tire contact. So I go like Thursday night, right? I'm driving around, right? It's snowing like crazy, right? I want to maximize the tire contact patch. When the car rolls, I want that thing, you know, it's only this big, right? That's your tire contact patch. 4 of those is what you have Thursday night. Okay? Scary. All right? So how do you maximize the tire contact patch? Well, if you take a regular car, you put it up on a lift, the wheels actually go through an arc as they go up and down. It's called wheel camber. It's one of the things that is adjusted when you get 4-wheel alignment. That's great. The first car we bolted our suspension into had wheel camber. So as we drove down a road, realized one of the goals of this car is 0 force into the car body. That includes counteracting all roll and pitch. So as you drive down the road, it doesn't roll. So that means as you go into a corner, the car just stays level. These things need to go up and down straight, but instead they were going through an arc. So the consequences is they were, as you drive through a pothole and this arcs, you get a lateral force. Think about that. You want a magic carpet ride, and every time you go over a pothole, you start going sideways. All right? That's not magic carpet. Okay? That was the next problem we did. All right, so a tremendous amount had to be learned about that. Why were we caught by that? Because if I go back to this model, the model wasn't accurate enough. The model didn't capture lateral or longitudinal inputs into the car body. All right, we had simplified it. And as you then go into the building part, you have to make the model more complicated. All right, so I want to represent, simplifying the model is where you get your insight from. Accuracy comes from increasing the complexity of the model. And you need to do both in practice and in experience. Okay, so that's all there is to it. So what I want to do is show you a quick video of what the car was capable of doing. All right, so what we did, the video I've got, we took 2 identical vehicles and we put one to the side, so one's a reference vehicle, unmodified, the other one was heavily modified. Now we started with a luxury sedan, all right? It is really important to listen carefully to the next few sentences, okay? We started with a luxury sedan, and most people think about cars as being a compromise between sedans and sports cars, right? You pick somewhere along the way. Sedans are pretty good in that they handle bumpy roads well, but they roll and pitch a lot. They give you motion sickness. On the other extreme are sports cars. They don't roll and pitch very much, but if you go down a bumpy road, my God, are they a rough ride. So what we wanted was a car that could do both of those simultaneously. So we started with a luxury car, okay, a sedan, and we modified it. But for a fair comparison, we had to go get a sports car. Now what you just heard is an argument you as an engineer can use to convince your management to go buy a sports car. Okay? Cannot emphasize these things important. These things are not. This is a useful tip to know. So I'll show you a quick video of what the car is capable of. Comparison between these couple of different cars. And the last little bit, if you have a bunch of engineers working on a project for a long time, you lock them in a room and you give them a video camera, they will do stupid car tricks. Yeah, I'll just leave it at that. So let's see if I can get the video.
Observe the performance of an unmodified luxury sedan with a factory-installed suspension. We're going to take the vehicle through a course that involves a lane change, braking, bumps, and slalom. Notice how the car body rolls and pitches through the course. Now, watch a vehicle of the same make and model, but modified to include the Bose suspension system, travel the same course at the same speed. Now, watch as the two vehicles drive side by side. Now, we'll drive a sports car through the same course. Next, we'll take the vehicles over a bump course. First, the unmodified luxury sedan. Then, the Bose suspension vehicle. And finally, the sports car. This bump course illustrates what it's like to drive over a very bumpy road. You can imagine which vehicle is easiest to control over these bumps. We're showing you how the Bose suspension handles a sustained turn. A conventional vehicle bangs outward during a turn, rolling away from the center, while the Bose suspension keeps the vehicle flat. But as part of our research, we've discovered a wide variety of ways to control a vehicle. What we'd like to do now is show you some of the other approaches we've explored. We'll tell the research vehicle to bank inwards, like a bicycle. And since we've programmed the suspension to vary the banking with the severity and direction of a turn, watch how the vehicle handles the slalom now. The Bose suspension has a tremendous amount of capability. Watch as the vehicle deals with this obstacle in the road. In slow motion, you can see how the car leaps over the obstacle. Of course, we have no intention of making these last few features available to the public in a finished product. Otherwise, you can imagine the boulevard on a Saturday night. But we're demonstrating them in order to show the flexibility of our approach. Our driver thanks you for your attention. And the Bose research vehicle thanks you.
All right. Now, let me be respectful. I know some people have a hard stop at 4 o'clock. So I just want to leave you with just a couple of things. First, the question I always get asked is sort of what happened, or what happens next. So these technologies, in general, involve modifying a vehicle suspension system. The suspension is a safety critical element in your car, so if it fails, you have a very bad day. So the level of safety validation is incredibly high. The costs associated with doing that are incredibly high. So Bose Corporation went through a process of working with a large number of vehicle manufacturers to build prototypes that show really impressive performance, and where things sort of stood was there was no sort of good first customer to work with to bring this to market because of the cost of the validation. It's also the case that fundamentally, unfortunately, electromagnetic systems are expensive. A lot of magnet, a lot of power, a lot of copper, all of these things that you have to deal with in real life engineering. So you need to look at ways of how do you take performance out of the system, cost out of the system. The last issue is weight. All right, the system fundamentally adds weight to a vehicle. Mass in a vehicle means your fuel economy is going to have a hit. All right. Now that said, as I can share, there are several active suspension programs I know of that are actively underway today. a lot of companies involved with this today. So it's still a very interesting and exciting technology. It's just something that Bose Corporation didn't end up moving forward in its particular day. However, a side effect is the realization that Bose had was that instead of suspending the entire vehicle, what if you just suspended the driver? So a product that did offshoot from this particular technology branch was something called Bose Ride, which is a seat for commercial truck drivers. So imagine the guys who drive 18-wheelers. Right? You don't need to suspend the entire 18-wheeler, but you can protect just the driver. Because it turns out professional drivers are exposed to very, very high doses of vibration and have a lot of health issues. So the idea was if you can protect the driver, they can drive more for longer periods of time, more comfortably, more safely, because they'll be more attentive. And that is an active area of business that Bose was able to commercialize the technology. And that continues to have a technology patent. So the big thing I want you to take away from this is fundamentally Bose Corporation, or more importantly, Dr. Bose. One of the things that struck me, and I was really fortunate, I got to work with him for over 20 years, was what I always thought it was a sort of a form of bravery, maybe the right word is audacious, in that he was interested in solving technical problems. Once he identified a technical problem, he didn't care what area it was in. And the reason was, it goes back to what Joel said during the introduction, is start with F equals MA. All right, equals C, D, V, D, T, 3 VEs out there. You can solve anything. It doesn't matter what discipline. So Dr. Bose himself worked in all sorts of different problem areas. I've been fortunate in my career, I've worked in lots of different areas, and these modeling techniques, these very simple techniques, are incredibly powerful and will allow you to solve problems across every possible discipline. So the big thing I'm asking each of you to take away is don't think of yourself as an engineer in just one discipline. You're an engineer, because you can solve problems in any discipline. Yeah.
More comfortable for the driver? You do put roads, you do build roads so that it's inner curve, so
Yeah.
it could be an advantage. I mean, again, you can imagine.
And a plane does that, right? When you fly in a plane, they always keep one G on it. The only issue that when we tried that, it turned out to be ridiculously not comfortable. Predominantly because you go in and out really fast, and you can't do a fully coordinated turn. So what would happen is, as a passenger, you felt like you were being popped up and down. It was very odd.
It was so counterintuitive to the brain was not expecting.
Yeah, I do think though that there is longer term, there is some good potential in the coordinated turns of vehicles. Especially when you start to look at autonomous vehicles where you don't have to, in this particular vehicle, you had a driver. Drivers are insane. They do just crazy stuff all the time. Autonomous vehicles have the advantage that there's no driver, or the driver is the same. So you can control what they do. So in those situations, I think there's quite a bit of potential for further performance improvement. It's a great question. Yeah.
Just one question I have. Did you guys ever think about like using a sensor to sort of sense the road's curvature and then try and optimize the suspension based on what's coming ahead?
Yes, we did. Let's see, just a couple of quick comments. Sensing the road ahead is always is sort of fundamentally challenging. And if you think about it, part of the reason is you're sending out, whatever you send out, whether it's light, infrared, LiDAR, what have you, it's coming back and it's a specular reflection back, right? So trying to gauge the depth of the pothole and you can't even see for the pothole is really, really tough. So getting pothole by pothole accuracy remains probably a little bit beyond any sensing system that I know today. That said, knowing the road ahead gives you a lot of clue, a lot of advantage. If you know that you're about to go up a hill or you're coming into a, let's say a parking garage, in a parking situation where you're going to go on a steep ramp, come over a sidewalk, knowing that in advance is hugely helpful. So the course knowledge in maps database is hugely advantageous. And again, a lot of companies, as they're looking into that today, are using that kind of technology. The only company that has something on the road that I know of, and you guys can talk to some of the other folks in the audience, I know, Mercedes has a system they call ABC, Active Body Control. Now it's actually, no, Magic Body Control, it's MBC. They're using look-ahead cameras. However, having ridden in that vehicle, if you blind the cameras, the performance seems to improve. Go buy a Mercedes and blind the cameras, and it'll ride really well. Yeah, don't do that. But I don't have a good system right now.
And Neil, you could imagine road learning today, right? If you go on the same route, the car knows where it is from a GPS point of view, it can measure the wheels, you can conceivably get better at driving your commute every day, and it'll know where the potholes are until they fix them. And it'll learn that too eventually.
So, and realize that autonomous vehicles, the way that they all navigate today, they have maps databases. All right. So most of the autonomous programs that are out there are working on, based on maps. Very few are 100% on just cameras. Most of them know where they are, and they're looking up in maps to know, when the next intersection is, where the stop lines are, something storing where the stop lights are, and things like that. So there's those rich map databases that will end up being really helpful for active suspension vehicles.
Are you guys just use a fully linear actuator as opposed to some kind of rotational motor?
Yeah. I'm wondering if I should answer that, or if I should let you answer that one. So the question is basically, how do you generate force? And linear actuation has, the reason that approach was originally taken was because it had very, very few negative side effects. Okay, it's sort of, you get force independent of position, independent of velocity. It's really a terrific system in terms of generating force accurately. It is not, however, the most efficient way to generate force. You need more magnet, more power, more everything. So you can start looking at other actuator ideas. I'm not really at liberty to share all the details of what Bose Corporation pursued, but I will tell you many companies have looked at rotary motors using a ball screw. And to use the ball screw to convert, you turn a nut and you sort of push the screw up and down. The challenge you have to deal with there, and by the way, it is a great approach. It has a lot of advantages. You can make the package much smaller, generate equivalent forces, but you have to deal with rotary inertials. Okay, so you spin this device up, and now when the road comes up and quickly turns around, you've got to slow that inertia down, so you have to use the actuator's own force to slow the inertia down and turn it around. So making a rotary motor into a really high-performance linear motor is doable, okay? But there's some overhead associated with doing that. And I will tell you, so I can share that there's a bunch of stuff in the public domain now from patents and papers. Many companies are trying that approach right now.
You mentioned one of the reasons why Bose stepped away from the project was cost. It was a big one. If you were still leading the project and if your goal was to reduce cost, would you have done it by decreasing force, decreasing bandwidth, or some other means of reducing complexity?
I kind of want another hand. I want another option, basically. So let me sort of answer the question this way: is the cost of these electromagnetic systems and high bandwidth systems is always going to be an issue. So the question is, how can you start to reduce some of the performance requirements and hide the limitations in some meaningful way? So as you point out, sort of the obvious things are, as you start to remove force in particular. Force is probably the single largest variable in an electromagnetic system because that's proportional to power. It sets what you need to do in terms of your power processing. It sets what you need to do in terms of the thermal performance of the system, all your dissipative issues also. So getting rid of force, reducing force matters. The problem is when you reduce force, you will get to points where you're giving up performance. So the question is, can you hide that? All right? And if you want to make a car that a human driver can drive and never get into a situation where they expose those force limits, you're going to have to make the force envelope pretty big. If you're willing to compromise the human driver experience a little bit, it's quite doable. Again, I'm going to play this card in autonomous vehicles. You have this opportunity to make sure that the driver never asks for more force than the vehicle has, and doing that in a coordinated way. So there's substantial cost savings that's available when you look at those types of systems. So to me, the biggest single variable is controlling the biggest unknown in the system is the human. And in this case, eliminating the human leads to some very big potential savings. So you can use some cost
Follow-up question
optimization.
then, does that mean, in your view, that active suspension is less viable in human-driven cars as a whole?
No, I don't feel that way. For me personally, the way I always look at the equation is, whenever you're an engineer working on a project, you're managing a ratio, benefit over cost. That's value, right? In any product I've ever worked on, benefit over cost, right? If the numerator is big enough, the denominator isn't such a big deal. If you're willing to accept that if the denominator is too big, the size of your market is going to be small. So do I think there's an opportunity? Yes, because what people will pay to get this level of benefit, I think is substantial. Right? My favorite examples are things like all-wheel drive. All right? Just out of curiosity, how many of you have all-wheel drive in your car? Okay. Any idea what your price penalty was for that? Maybe $2,000 to $3,000. Customer cost, right? How many of you use the all-wheel drive on any day except last Thursday? It's a benefit that people want. They will pay for it. You're not even using it that much. You're willing to have it. Active suspension is unique in that every ride, every moment of every ride, it's delivering benefit. So the benefit potential, I think, is enormous, and that justifies fairly.
Just to tag on to that, and this is something that a lot of engineers perhaps tend not to think about as much. The automobile is at the end of a 100-year pipeline of optimization, to where when they mine the materials, they're already mining them with it in mind about what kind of steels have to be used in the car. And so a car actually ought to cost several $100,000 at a minimum, if you think of it as a lower volume device. And the cost comes down because of the volume. So you have a chicken and egg problem with any new device that you introduce. It would be interesting to know what the cost of that, I mean, I know high bandwidth devices are likely to be more costly, but if you were manufacturing them, if you had the quantity, the scale, and the 30 or 40 years, let's say, to get the process and the suppliers underway, that cost would come down significantly.
You know, there's many people in the audience who are interested or working in the area of robotics. And robotics is a great example where people are always interested in different actuation systems. And it's a question of force density, power density that you can put in actuators. And if you look, robots today still look pretty expensive. But if you melt down the material costs of what go in, right, they're not the raw cost of the copper, the steel, magnetic material isn't actually all that high. Right, but we're not at volumes yet that can bring us down these price curves.
Absolutely.
Yeah. So, and that's what's interesting about automotive. It's area. If you sell into the automotive industry, you're going to sell hundreds of thousands of copies. Okay.
Did you ever consider a hybrid system in terms of a certain performance on the wheels and then putting the seat system in?
Yeah, we refer to that as the whooper-tweeter solution. Yeah. So I can share. So Audi has announced they'll be shipping. Actually, should be available just about now on the new A8. So they're doing a hybrid system right now where they've got a electromagnetic anti-roll bar. So relatively high value. I think it's like 2 or 3 hertz. Anyone actually measured it? Anyone?
They claim 5.
Sorry?
They claim 5.
They claim 5, yeah. So they're doing the cancellation of the roll degree of freedom using that, and then they have a motor associated with each wheel to do then some of the vertical cancellation. So those, if you will, that's the, if you will, the tweeter, and then the roll bar is doing the whooper piece of that, the low frequency piece. So you are starting to see crossover solutions out there.
So the active seat comes into play?
So the question is, if you combine some of the active suspension, suspend the whole vehicle, then you do a secondary isolation of seat. Again, what I can share is I don't know any commercial product that's shown that. I do know of several research projects that are using that for that. Or variation of that.
If you were to define a comfort function, what would it be?
It's a great question because, it's funny because we would hire several engineers to sort of say, okay, go work on a comfort function. Because if they invented one, man, that was gonna be great. We'd really love that. I will tell you the moment when I realized it was going to be futile. Let me explain it that way, because the answer I have no idea to this day. But I'll tell you the moment I got just utterly depressed. Okay, I'll share that story. So we were out and we were driving a particular road, and we were going over a hill crest, and the car would get to end of travel and it would be uncomfortable. And we were trying to figure out why it was uncomfortable. So, not knowing any better, what we did is we put a button on the car, and the idea was that when you went over the event and it was uncomfortable, you'd hit the button, right? And then what we do is we go back and we look at all the traces we had accelerometer all over this car, so we know everything there was to possibly know about what was going in there, right? So all we had to do was look at the button press. So, I actually was the first person I think that pushed the button, so I pushed the button. When I went over the event, it was uncomfortable, I hit the button, I tried to time it to the best of my ability. We went back, we looked at the traces, they were perfectly smooth. Couldn't see a bloody thing. No, that was annoying. Okay, but we knew where we were along the road, so at least we knew where the event happened. So that was at least something. But there were other people in the car, so we did it with the next person in the car. Okay. The project was Bill. Bill then hit the button when he said, "It's uncomfortable." He hit it at a completely different time than I hit the button, by like half a second. Okay, and it should have been within tens of milliseconds. So he hits at a completely different time. This was not good. All right, then we had a third guy. The third guy for the same experiment. He hits the button. He hits it half a second earlier, yet still. Okay. So all three of us realized we decided it was uncomfortable at different times, varying by over a second, and no trace that we could ever identify on any signal anywhere ever told us where the discomfort was. Okay, that includes seat accelerometers, things under our butts, nothing. We could never figure out, and this was, everyone repeatedly said it was uncomfortable every time. I don't know how to make a company. Okay, and I got to tell you, I see so many great papers on how to how to make a comfort meter. I see hundreds of them. Yeah.
Just thinking this, like, when you think about the driverless cars, the utility of the car not shaking is going to increase much, because then you're going to be using the car for doing work for the 3 hours, 4 hours of driving.
Yep.
So that's one effect, I would say, that's going to drive the importance of this technology, or the importance of comfort. And the other thing is that an average car is used less than 5%, utilized less than 5% of the time. So now I'm willing to take, let's assume perfect utilization, 25 times.
Yeah.
So actually I'm willing to accept a 25 times higher price for the blow.
Yes.
Right, so there's also, if you build in like some parts where the car is not utilized, still price is going to be covered by many more customers. So it's going to increase both the value and acceptance of the higher cost.
I completely agree. And look, the model is already in existence. You have this with Uber today, right? You can get an Uber Pool. If you want to pay for faster time, you can get an Uber X. If you want a nicer car, you can buy an Uber Black, right? So you're already choosing. As you point out, when people start saying, hey, now, for instance, what if you start, Uber starts to introduce, I don't work for Uber, let me think about it. I'm offering this as a business scenario for them, but what if I could have, my car shows up and it's got a full VR rig associated with it, and I could be gaming the entire time.
how do you sort of subscribe to different features like that? But even today, I mean, you can subscribe to cars. There's already a notion of joint ownership of cars, so people are going and buying, 5 people will buy a car and doing car sharing amongst them. So I completely agree with you. Cars are no longer, you buy them and they spend most of their time parked. They will become assets that are doing more work for people. So, it'll be interesting to see how automotive transforms in the coming years. Thank you. Okay. Thanks for putting all the right on.
You're not going back to the office, right?
Yeah, I'm gonna take the stuff back. I have my keys up there.
Oh, you are?